Hi everyone, this is Mrs. J, and today we're going to learn how to find the average value of a function. I do have a quick warm-up for you guys, so please pause the video and give it a try. All right, go ahead and check your work here. So we have two different volumes created by cross-sections. So here's the base of our volume. This cross-section is a semicircle perpendicular to the x-axis. So here's the base of my semicircle, and I can see that I'm integrating side to side, so with respect to x. So the diameter of that semicircle is x squared minus 0. So the radius is half of that, and I know that the area of a semicircle is 1/2 pi r squared. So then I'm going to take that and integrate it from 0 to 2. I always pull my constants out, and you should end up with 4 pi over 5. Now for the second one, we have equilateral triangles as our cross sections, and it's perpendicular to the y-axis. So for this one, we need to find a way to define the area of an equilateral triangle in reference to its base or one of the sides. So you can see I did that work over here. We did this in the last lesson as well, but the area would be root 3 over 4 times the side squared. So we just need to define our side length, and we are integrating with respect to y, because if this is your cross section, we have to slide it up and down. So we need to define this with respect to y. So it will be 2 minus square root of y, which is this equation in terms of y. So here's the area of our equilateral triangle, and then I'm integrating that from 0 to 4, again pulling out my constants and then evaluating. You should end up with 2 root 3 over 3. All right, so first thing we're going to talk about in this lesson is the average value of a function. So the average value of a function is the value that would produce the same area if the function were a constant rather than this curve. So there's a formula for this, but I want to make sure we understand, what this actually means. So we're going to go through an example. So let's take this bounded area here. If I want to find this bounded area, I'm just going to define this height and integrate from left to right. So I'm going to integrate with respect to x. So that height here, the height, or I'll call this h. This height is just 1/2 x squared minus 0. And again, I'm just integrating that from 0 to 3. And I'm going to pull my constant out front. So we get 1/2 times 9, so 9 halves. So that's the area under the curve. But we're wondering what value, so what y value or what height would give us the same area of 9 over 2. Again, if rather than being this quadratic function, it was just a constant function. So I'm working with the same width as my base, so it's still going to be from 0 to 3. But I'm wondering what value, again, or what height, we'll call this y, would produce the same area, which is 9 over 2, if it were constant. So I'm essentially saying, when is 3y equal to 9 halves? So then that's when y is 3 over 2. So if my function were the constant function, y equals 3 over 2, this area would look like this, and this area here is the same as the area under my curve over that same interval of 0 to 3. So this y value is considered the average value of our function. So that's what we will be trying to find today. So to kind of generalize this into a formula we can use, if you look at what we did here, we took the area under our curve and we divided it by the width of our of our interval, so the base of our interval essentially. So we could say that the average value is always going to be the area divided by the width. And then of course we know that that area is just the integral from a to b of f of x dx. And we can define the width as b minus a. So the formula that we typically see for the average value of a function is 1 over b minus a times the integral of a to b of f of x dx. So this value, if we do all of this, the value that we get will be a y value, and it will be considered the average value of our function. But this is where, this process is where this formula comes from. So it's important to understand what exactly you're finding. Again, you're finding the height that would produce the same area as the area under the curve if your function were a constant rather than that quadratic or whatever type you're working with. All right, let's try one of these together. Here we want to find the average value of f of x equals square root of x on the interval 0 to 4. So we do a quick sketch of this. And here's 4, and so we know that this is 2. And here's our area. So again, what we're asking essentially is what y value would give a rectangle the same area as the area under this curve. That's what we're asking. So we're going to use our formula for this. So 1 over b minus a, and then we'll do the integral from a to b of f of x dx. So we can see that our b value is 4, our a value is 0, and we're integrating from 0 to 4. And then here, this distance is just square root of x dx. And again, once we actually simplify this, that value will be the average value. So here we have 1/4 times 2/3 x to the 3/2 evaluated from 0 to 4. So 1/4 times 2/3 times 8. So that ends up giving us 4/3. So this is the average value of our function. So it's essentially saying if I took this height of 4/3, let's say it's about here, and I turned that into a constant function, so a rectangle over that same interval from 0 to 4, this rectangle has the same area as the area under our square root function from 0 to 4. So again, we found the y value that achieves this scenario. All right, I have one for you to try on your own, so go ahead and pause the video and give it a shot. And for this one, you actually don't need to graph it. You can just use the formula to find this average value. All right, go ahead and check your work here. So our average value, which is sometimes denoted as f of c, is 1 over b minus a times the integral from a to b of our function, which is just the area under the curve. So again, you don't actually need to sketch this out in order to find this. So here I have my antiderivative, and I'm evaluating from -1 to 2, and then you end up with -3 over 2. So again, if I drew a rectangle, where this was the height, the area of that rectangle would equal the area under this curve. All right, so now that we know how to find the average value of a function, we're going to talk about the mean value theorem for integrals. So maybe you'll remember MVT for derivatives. Which we learned about in first semester. Essentially saying that somewhere over a differentiable and continuous curve, the slope of your secant line will be equal to the slope of the tangent line, at least somewhere, maybe more than once. So this value is what we were trying to find. We were trying to find the x values where, again, the slope of our tangent line was equal to the slope of the secant line. Now for the mean value theorem for integrals, this one says that if f is continuous on this closed interval, there exists a number c within that closed interval such that, well, we see the integral from a to b of f of x dx. So again, this we know is just the area under the curve. And I want to just draw a little picture of this down here so we can look at it as we go. So here's our function. Let's say this is our function, and here's A, and here's B. So the area under this curve is equal to f of c, which we know just represents the average value of our function. And we know that b minus a is the width of our rectangle. So if I were to draw that out, maybe here's f of c. So this distance is f of c. And then we have over a minus b. So again, we're saying essentially if we do f of c times a minus b, this entire thing just represents the area of the rectangle. So what we're trying to find in this case is the c value right here. We're trying to find this c value. So the c value that essentially corresponds with the average value of our function. So this time we're not finding the y value. We want to find the x value that corresponds with that average value. That creates that scenario where the area under the curve is equal to the area of that rectangle that's created. So again, that's the mean. The mean value theorem guarantees that there exists some c value where this scenario would happen. Again, that the area under the curve is equal to the area of some rectangle that, whose height we call f of c. So again, with MVT for integrals, we are finding this c value. All right, let's try one more example together. So here we're considering this function 1 plus x squared over the interval -1 to 2. So we're going to start by finding the average value of that integral, or the average value over that interval. So we'll use our formula. So f of c equals 1 over b minus a, so 2 plus 1, and the integral from -1 to 2 of 1 plus x squared dx. And then we'll just simplify that. So we have x plus 1/3 x cubed from -1 to 2. And if you evaluate that out, we get that f of c, which is, again, our average value, should equal 2. So again, I'm kind of skipping the steps of fully evaluating this integral, but I know you guys can do that part on your own. All right, and now for part B, we want to find that c value that is guaranteed by the MVT for integrals. So again, we're just finding the x value that corresponds with this height. So we're just taking this height and setting it equal to our original function. So we want to know, again, the x value that generates that y value. So here we get x squared equals 1. So we actually get two values here. X equals plus or minus 1. So those c values, again, we'll just call them c, are plus or minus 1. So there's actually two values that work for this problem. And then for part C, we're going to sketch a graph of this just so you can kind of visualize what's going on here. All right, so for our quadratic over that interval, we know the vertex is at 0, 1. So here's our curve. So we know we already found that average value. We said that the average value is 2. So we know that at y equals 2, if I turn that into a rectangle with the same width, like this, the area of this rectangle, here in red, is equal to the area under the curve here in blue. Okay. So again, this is at 2. And then we wanted to find those x values that generate that average value. And again, it's when it is also equal to our curve. So you can see here that that's happening here at -1 and here at +1. So there are actually two c values that give us this height, which gives us the average value of our function. So hopefully this kind of ties together, what the average value is and then what the mean value theorem for integrals guarantees. So what you're trying to find for that. Okay, that is all for today's video. Thank you so much for watching.